Hey everyone, this is Subhashni from Artificial Intelligence and Data Science of the first year. In this video, we are going to see about the DST lab experiments. By the way, the first experiment is the study of logic gates. In the logic gates, first we are going to see about the AND gate. The AND gates connections are represented based upon the logic diagram. Let's see about the connections. When the two switches are 0, the output is also 0. When the B is 1, the output is 0, and when the A is 1, the output is 0, and both the A and B are 1, the output is also 1. Then by replacing the AND gate to the OR gate, we need two switches same as the AND gate. When both the A and B are 0, the output is also 0. When B is 1, the output is 1. And when A is 1, the output is 1. When both A and B are 1, the output is also 1. Then the connections for the NOT gate is given based upon the logic diagram, and when the input is 0, the output is 1, and when the output is 0, the input is 1. It is the vice versa. For the XOR gate, we need two switches, a XOR gate and a bulb. When A is 0 and B is 0, the output is also 0. When A is 0 and B is 1, the output is 1. And when A is 1, B is 0, the output is 1. When both A and B are 1, the output is 0. For the NAND gate, when both the inputs are 0, the output is 1, and when B is 1 and A is 0, the output is 1, and A is 1, B is 0, the output is 1. When A and B is 1, the output is 0. For the 3 input NAND gate, when A, B and C are 0, the output is 1, and when A is 1, the output is 1. When B is 1, the output is 1. When C is 1, the output is 1. When A and B is 1, the output is 1. When B and C is 1, the output is 1. When A and C is 1, the output is 1. But when A, B, C are 1, the output is 0. When both the inputs are 0, the output is 1. And when A is 1, the output is 0. When B is 1, the output is 0. When A and B are 1, the output is 0. Now let's move on to the second experiments of study of adders and subtractor. For the half adder, we need two switches, an XOR gate and the AND gate. The two outputs are the sum and carry. The first one is sum and the second one is carry. Okay? And when the two inputs are 0, the output is 0. When the A is 1, the sum is 1. When B is 1, the sum is 1. When both A and B are 1, the carry is 1. This is the logical representation of the full ladder. We need 3 switches, 2 XOR gates, 2 AND gates, 1 OR gate, and 2 bulbs for the output. The output are sum and carry. The first bulb is sum and the second bulb is carry. When A is 1, the sum is 1. When B is 1, the sum is 1. When C is 1, the sum is 1. When A and B are 1, the carry is 1. When B and C are 1, the carry is 1. When A and C are 1, the carry is 1. When A, B, C are 1, the sum and carry are 1. This is the logical representation of half subtractor. For half subtractor, you need two switches, one XOR gate, one NOT gate, one AND gate, and two outputs of borrow and difference. The first bulb is the difference and the second bulb is the borrow. When both A and B are 0, both the borrow and difference are 0. When A is 1, the borrow is 0 and the difference is 1. When B is 1, the borrow and difference are 1. And when A and B are 1, the borrow and difference are 0. Let's move on to the full subtractor. For the full subtractor, you need 3 switches, 2 XOR gates, 2 NOT gates, 2 AND gates, 1 OR gate, and 2 bulbs for the output. The output are the borrow and difference. The connections were given based upon the logic diagram, and the connections are checked based upon the truth table. Let's move on to the third experiment. Design and implementation of code converter. In that we are going to see about the binary to gray code converter. For binary to gray code converter you need 4 inputs, 4 outputs, 3 XOR gates. The 4 inputs are B3, B2, B1, B0. The 4 outputs are G0, G1, G2 and G3. Let's give the connection. Hence the connection given is completed, and now we can refer the truth table and check whether it is correct or not. Next one is gray code to binary code converter. For this you need 4 inputs, 4 outputs. The inputs are G3, G2, G1, G0. The outputs are B3, B2, B1, B0. In additional, we need 3 XOR gates. Now the connection given is completed, and now we can verify it based upon the truth table referring our node. Check it whether it is correct or not. Let's move on to the fourth experiment. The fourth experiment is design and implementation of code converter 2. In this, we are going to see about BCD to XS3 code converter. For this, you need 4 inputs B3, B2, B1, and B0. The circuits we need are two XOR gate, two OR gate, one AND gate, two NOT gates. We get 4 outputs. Now the connection for the BCD to XS3 code converter is completed. Now we can check the connections are correct or not based upon the truth table and verify it. And that next one is XS3 code to BCD code. For this you need 4 inputs x4, x3, x2, x1, 2 AND gates, 2 OR gates, 2 NOT gates, and 2 XOR gates. Give the connections. We get 4 outputs. Connect to the output perfectly. The outputs are referred based upon the truth table. Now verify it with the help of the truth table. Now let's move on to the fifth experiment. The fifth experiment is design and implementation of parity generator. For this you need two inputs A and B, two XOR gates, one NOT gate, two outputs. Connections are given. Sorry, three inputs. The truth table is given as 000 is 10, 001 is 01, 010 is 01, 011 is 10, 100 is 01, 101 is 10, 110 is 10, 111 is 01. Here we reach the final experiment. It is the design and implementation of multiplexer and demultiplexer. First, we can see about the multiplexer. For this, you need two inputs, four data inputs, and we get only one output. Let's take two switch. We need two NOT gates, four AND gates, and one four input OR gate. Output is connected to the bulb. One zero, sorry. 00 is 1 and 01 is 1, 10 is 1 and 11 is we also came to the 1. Final part, demultiplexer. For this we need two inputs, one clock and two NOT gate, four AND gate and four outputs. The connections are given. Hence the connection is completed. Now we can verify it based upon the truth table and check whether the given connection is correct or not. Let's move on to the seventh experiment. The seventh experiment is design and implementation of encoder and decoder. The connections are given based upon the logic diagram for encoder. First, we have connected with use of 7 switches. For the output, we are connecting to the 3 bulbs. We are using OR gate for the result. When Y1 is 1, the output of the C bulb is 1. When Y2 is 1, the output of B bulb is 1. When Y3 is 1, the output is B and C is 1. When Y4 is 1, the output of A is 1. When Y5 is 1, the output of A and C is 1. When Y6 is 1, the output of A and B is 1. And when Y7 is 1, the output of A, B, C are 1. The connections were given based upon the logic diagram for decoder. E, A, B are the three inputs. We are then connecting to the NOT gates. For the output, we are connecting to the 4 bulbs. The outputs are D0, D1, D2 and D3. From the switch, it is connected to the 4 AND gates, and the connections were given based upon the logic diagram for decoder. The decoder is the reverse of the encoder. When everything is 0, D0 is alone 1. When E is 1, the output is 0. When A is 1, the output of D2 is 1. When B is 1, the output of D1 is 1. When A and B is 1, nothing close. The final experiment is study of flip-flop. In the flip-flop, we will see about RS flip-flop, JK flip-flop and D flip-flop. This is a logical representation of RS flip-flop. First, for the RS flip-flop, we need 2 switches, 1 clock, 4 NAND gates and 2 bulbs for the output. When the S and R are 0, the output is also 0. When R is 1, the next state is 1. When S is 1, the present state is 1. When S and R are 1, the present state and next state is 1. This is a logical representation of D flip-flop. For D flip-flop, we need 1 switch, 1 NOT gate, 1 clock, 4 NAND gates and 2 bulbs. When the input is 0, the next state is 1. When the input is 1, the present state and the next state is 1. This is the logical representation of JK flip-flop. For JK flip-flop, you need 2 switches, 1 clock, 2 NAND gates with 3 input, 2 NAND gates and 2 bulbs for the output. Thank you guys. Meet you later.